Okay, we're going to look at coordinate vectors. So what we need for this is we need to have the coordinates of points on a Cartesian plane to start with in 2 dimensions, and in the 3 dimensions we have the three-dimensional axis system, which we'll get into. So for first look at this, if we draw in the xy axis and we put in a point 3, 2, could be any point, let's just choose 3, 2 for the sake of this one, and we draw a vector from the origin to the point 3, 2. This is called the vector 3, 2. So the vector 3, 2 goes from 0, 0 to the point 3, 2. From the origin 0, 0 to the point 3, 2. It looks very similar to just the point 3, 2. There are other notations that you can use for vectors. Sometimes you write the coordinates as if it's a point with a line over the top to make it a vector. For our textbook, it just leaves it as 3, 2 without a line over the top. So you have to be able to tell within the context of the questions whether we're talking about a vector or a point. Okay? So that is a point, so a vector from the origin to a point. All vectors in 2 dimensions will be viewed as if they start from the origin. Even if they start from another point and go to some other point, they will be looked at as if they start from the origin. And I'm going to explain that now. Okay, so state the following vector in coordinate form. All right, so the vector from point P, which is -1, 3, to point Q, which is 4, -2, well, clearly we can see that the vector goes from that point to this point with the head of the vector right here. Okay. But now we have to think of it as being translated to the origin. So point P is translated to the origin so that we can think of it as a vector starting from the origin. Okay. If we do that, we're really just looking at the rise of this, or the height of this, vertical height of this line, or the vertical component of that vector, and we're actually going down 5. So -5 is what you're going down by, and then you're going across 5. So from on the y, from 3 to -2 is going down 5. From -1 to 4 on the x is going across 5. So if we take this whole thing and translate it down to the origin, this is what we get as the vector here. So the vector PQ is equivalent to the vector from the origin to the point 5, -5. Okay, so we call the vector PQ is 5, -5. Another way of looking at this, in fact the most important way of looking at it, when we start writing these things out, is if we take a look at these 2 points, okay, P and Q, so the same points that we had before. P is -1, 3, and Q is 4, -2. If we then take a look at the vectors from the origin to those points, so OP is the vector -1, 3. Okay, so now -1, 3 represents a vector. The last point, last diagram, -1, 3 represented a point. Okay, so OP means from the origin to point P. That's the 2 points. And OQ is the origin to point Q. Now if I look at these 2 vectors, like this, okay, are starting at the same point. So the vector joining the tips of those is really just using the parallelogram law, and it's the diagonal joining the 2 endpoints of the vectors, which is a difference of 2 vectors. And because it ends at point Q, the vector PQ is OQ minus OP. That's using the parallelogram law. Okay, so we have vector PQ equals OQ minus OP. Okay, so we always begin with where the vector ends. So it ends at Q, so we're going to begin with OQ. And we're going to subtract OP. And that's from the parallelogram law. So in this case, if we do that, well, OQ is is 4, negative 2. Okay, and OP is negative 1, 3. When we subtract these vectors, well, 4 minus negative 1 is 4 plus 1, which is 5. And negative 2 minus 3 is going to be negative 5. Okay, and we get the same answer as we got from the previous example just by physically moving the vector. This formula always works. Vector PQ is OQ minus OP. In 3 dimensions, well, it takes a little bit more effort to graph this out. Okay, so here's what I got. In 3 dimensions, when you draw a 3-dimensional axis, okay, so you've got X, Y, and Z. Let's just draw this out for you again. Okay. So X is now coming out of the page. Okay. Y is going horizontally on the page, and Z is going up. Okay, so that is the right-hand coordinate system, it's called. And if you want to plot a point in 3 dimensions, well, you kind of have to draw some stuff on the axes. Okay, so in this case, if you want to plot the point, let's see what it is here, 5, 3, 8, or 5, 3, 2, sorry. So the point 5, 3, 2, well, you're going to go 5 units on the x-axis, so let's say 5 units is there. Then you're going to go 3 units on the y-axis, so let's say 3 units is there. And 2 units on the z-axis, so it's 2 is there. Okay, so the first thing you want to do is draw the sides of a rectangular prism. So I'm going to make this side here, I'm going to draw that by going straight up parallel to the z-axis about 2 units, and then draw that across there, and that will give me a point called 5, 0, 2. Now this point here, that point is 5, 0, 0. Okay. This point here is 0, 0, 2. And this point here is 0, 3, 0. Okay. So now we're going to go across here to the back of the rectangular prism. Go down. Okay, so this edge here is going to be parallel to this one here is parallel to that. Okay, and that point will be 0, 3, 2. Okay, then we want to put this edge parallel to that one. This one parallel to the back edge. Okay, that point will be 5, 3, 0. So 5 on the x, 3 on the y, 0 on the z. And then we're going to complete the top part of this. So I'm going to go over here down here, complete that, and that point now is 5, 3, 2, and that's how we plot a point in 3 dimensions. It can be done much quicker. You could just go 5 on the x, make a line from there across to 3 on the y, and then up parallel to the z-axis 2 units. So really you only have to make this line and this line to get that point. But to visualize where it is, it's nice to see the rectangular prism. Okay, so that's the point. Now, once we have that, we can draw in the vector, which may be otherwise hard to see. That is the vector that goes from the origin to that point. So that vector is 5, 3, 2, and that's a vector. Okay, and that vector goes from the origin, which is 0, 0, 0, to point P. Okay, so that's point P. So that's equal to OP. So there's a vector in 3 dimensions from the origin to a point. Now if you had to do a vector from 2 points that are not at the origin, then we have something that's going to look like this. Okay, so if you want to get the vector from point P to point Q, here's P. P is 3, negative 2, 1. Q is negative 5, 1, 4. So to draw them, so I'm going to go 3 on the x, negative 2 on the y, 1 on the z. There's my point P. There's my vector OP. Okay. For Q, I'm going to go negative 5 on the x, so I'm going to go this way on the x. I'm going to go 1 on the y, so I go across here, which is parallel to the y-axis, 1 unit. And then I'm going to go up 4, parallel to the z-axis, and I've now got point Q. Okay. The vector from the origin to point Q is OQ. Looks like this. Now I've drawn a rectangular prism that encompasses those 2 points as opposite vertex. The diagonal in that prism is the vector PQ. Okay? So it's as if you have to translate this point P back to the origin here. And if you did that, if you take the negative 5 in point Q and you translate it 3 units backwards, because you have to move this back 3 in the x, negative 5 turns into a negative 8. Okay? And the 1, I'm going to translate it 2 units. It's already negative 2, so I'm going to 2 units positive, so that's going to go from 1 to 3. And 1, I have to translate that down 1 in order to get that to the origin. So I'm going to translate that down 1, which is going to give me another 3. So that ends up being the coordinates of the vector PQ. If we look at it in the same, more algebraically, in the same way that we did before, PQ equals OQ minus OP, which is true. PQ from tip of the vector OP to tip of the vector OQ, that is a parallelogram law again. So it's going to be PQ equals OQ minus OP. Same rule works in 3 dimensions as it did for 2 dimensions. And when you fill in these coordinates of the vectors, negative 5, 1, 4 is for OQ, 3, negative 2, 1 is for OP. These are now vectors, not points. Subtract them, you get the same answer that we did when we looked at it logically and translated it above here. Now, if we look at direction and magnitude of these vectors, so we've got direction, okay, and magnitude. So a vector in 2 dimensions. Let v equal 3, 4. What is the direction and the magnitude? Okay. So the magnitude, if we draw the vector 3, 4, there it is, from the origin to the point 3, 4. Its magnitude is just using Pythagorean Theorem. 3 in the x, 4 in the y, so the magnitude is 3 squared, root 3 squared plus 4 squared, which equals 5 for this one. The direction, well, we can look at the direction in terms of an angle with the positive x-axis. Well, that angle is tan of theta is opposite over adjacent, so theta equals tan inverse of 4/3 for this one. And you get 53.1 degrees from the positive x-axis, going counterclockwise. In 3 dimensions, okay, so the magnitude of this vector in 3 dimensions, 3, 4, 2, well, if we draw it, we've seen this kind of thing before. If we draw this vector, we're trying to find the length of this. Okay, so 3, 4, 2. I also drew that line over there. This diagonal on the bottom of it's like a shadow of this vector down on the x, y plane. Okay. So it's kind of like the shadow of this vector down on the x, y plane. So this is the hypotenuse of a right triangle on that xy plane. And you can find the length of it using Pythagorean Theorem. And then using that and this side, you can use Pythagorean Theorem again, because that makes a right angle with this line here, with the z-axis. So you Pythagorean Theorem again to get the magnitude of v. Okay. So this is just what I was saying. You got a, which is this line here, equals root 3 squared plus 4 squared, which is 5. Okay, using that right triangle there at the bottom. And then once you've got that, use Pythagorean Theorem again with the 5 and the 2, and you get root 29. Okay. Otherwise, we can use what we developed before, the 3-dimensional Pythagorean Theorem, which is magnitude of v equals square root of x squared plus y squared plus z squared. Okay, so if it's from the origin, then or you have the coordinates of the vector, which you do, then you're just going to take and plug it into that formula and you get root 29. Talking about the direction of this vector is a little more complicated. There's a number of different directions. You could say that the angle between that vector and the xy plane is one of the direction entities of it, and then the angle with the yz plane would be another angle, and that would be enough to give it a direction. But what we tend to look at right now is we think of the vector 3, 4, 2. Well, we've got coordinates. If I change any of those coordinates, it goes in a different direction. And we can picture the direction of it based on the coordinates. So that's often enough. But we will get into something called the direction angles and direction cosines later on, where we find the angle with each of the axes. So the angle with the x-axis, the y-axis, and the z-axis. Okay? And so that's how we find the magnitude of a 3-dimensional vector. And then we have these vectors that we need to mention, the I, j, and k vectors. They're unit vectors in the direction of each axis. So I is a unit vector, 1, 0, 0. So it's length 1 along the x-axis. J is length 1 along the y-axis. K is length 1 along the z-axis. If we had this in 2 dimensions, we would only look at I and j, and we wouldn't have the third coordinate. Okay? So that would be it in 2 dimensions. This is more general in 3 dimensions. Okay? So here's a question. Does v equal to 7, negative 3, 5 equal 7i minus 3j plus 5k? Many of you will look at that and say, yeah, that makes sense. Okay. And here is a fairly simple proof of it. So you take the right side, 7i minus 3j plus 5k. Plug in the vectors that we've just defined, 1, 0, 0, 0, 1, 0, 0, 0, 1. Multiply the 7 and 3 and the 5 in, add them up, and you get 7, negative 3, 5, which is the vector that we wanted. So yes, it is true. Okay. Now, and here's a little sample question from page 325. X equals 2i minus j, y equals negative I plus 5j, and they want you to simplify this formula. So, and this is how we work it out. Fairly straightforward, algebraically. And I believe the book ends here, but if you ended here, that's fine too. And that's it for this lesson.